talking to us about a tidal origin for Kepler-221.
Hi guys, I'm Max Goldberg from Caltech, as you heard, and I'd like to talk with you about a project I've been working on with Konstantin Batygin here at Caltech on a really unusual Kepler system called Kepler-221, which may be able to shed light on how super Earth systems are assembled in general. Also, I should mention I'm giving a modified version of this talk next week from my qual, so I'd really like to hear feedback and tough questions because I'd rather hear them from participants here than from my qual committee. So you've heard a lot about Kepler in this conference, but the important thing for me is that Kepler gave a really good census on close-in planets. Particularly, it found lots and lots of planets in between Earth and Neptune in size, and a lot of several hundred multi-planet systems with a bunch of these planets very close to their star. And that was just because Kepler stared at a lot of stars. And there's a special type of these systems called resonant chains. So if you look at the ratio periods of adjacent planets, sometimes those ratios are ratios of small integers like 3:2 or 8:5. And so you have these famous resonant chain systems like Kepler-80 or TRAPPIST-1. But those only represent a small fraction of the total number of systems. So there seems to be some sort of resonant, non-resonant dichotomy in the transiting sample. Most systems are not really resonant, or they have maybe one resonance or some tracer of that, but they're not a resonant chain. But there are resonant chains, and they've generated a lot of research interest because they provide some clues about formation. But this is actually kind of a problem. So you have this distribution of planet orbital period ratios, and you definitely see peaks near 3:2 and near 2:1. You see that resonances are important, but they're not common enough. And why this is a problem is, just as we heard in the previous talk from Brandon, migration is kind of inevitable. So planets, we think, form in a gaseous disk, and those disks drive migration immediately. And migration, convergent migration, leads to orbital resonances. If you have two planets and they sweep through an orbital resonance, in most cases they capture into it and remain in that resonance. So we expect resonances to be very common, but really they're uncommon. So something's going on that's either disrupting the resonances or preventing them from forming in the first place. So this is a serious problem in multi-planet dynamics. There are a few hypotheses. So one is to say that maybe the resonances don't form in the first place. There's some problem in migration that causes them not to form, but that doesn't seem to work so well. It doesn't really reproduce the observed distribution. A more successful scenario is to say that instabilities occur after the disk dissipates. So you have a bunch of embryos that come together and they form in resonances. And then the gaseous disk dissipates. You lose the eccentricity damping that controlled the instabilities. And then suddenly the planets, their orbits cross and they collide, and that leads to non-resonant systems. And that seems pretty successful as long as that happens like 95% of the time, and then 5% of the time it doesn't happen, and you're left with these resonant chains that didn't undergo a collision. But I'd like to step back and ask a more fundamental question, which is that, are these systems, these resonant chains and the not resonant chains, are they fundamentally different? Did they form in a different way in the first place? Or is it the case that one evolves into the other some of the time? And if that's true, then what exactly is going on when a resonance is lost? And what if the resonances are actually still there and they're just hiding in seemingly non-resonant systems? So what does this have to do with Kepler-221? Well, I want to spend the rest of the talk talking about this particular system. So in many cases, Kepler-221 is kind of an unremarkable four-planet system, and it hasn't had a specific study on it. It's a G-dwarf with 4 planets detected in the Kepler pipeline. The innermost planet is a super-Earth, 1.7 Earth radii. It has a pretty short orbit of less than about 3 days. The other 3 planets are sub-Neptunes, a bit under 3 Earth radii, but we don't have masses for this system, and I'll get back to that. But there are no obvious orbital resonances here. So the period ratios are here. The period ratio between the 2 innermost planets is 2.035, which is a few percent wide of 2, of a 2-to-1 resonance. But that's kind of outside what you consider to be an active resonance. Maybe it's connected, but it's not really in resonance. There is one kind of interesting thing about this star, which is that it has a high lithium abundance and activity in its calcium lines. And both of those are markers of youth. And in fact, this star is no more than a gigayear old and is probably about 600 million years old, which is pretty unusual for the Kepler sample. It's in the bottom 5%. So that's kind of strange. We actually didn't realize that at first, only later. But that's not why we're not studying this system because it's young. We're studying for another reason, which is that it has a three-body commensurability. So a commensurability is a relation between the orbital frequencies or periods of the planet. So the commensurability for Kepler-221 looks like this. So n here is the mean motion, which is basically 1 divided by the period or the orbital frequency of the planet. And we have, in 3 planets here, have this relation where you have 2 times n of B minus 5 times n of C plus 3 times n of E is a frequency that is very close to 0. And this is not a coincidence. And so this is kind of related to how we typically describe orbital resonances. But when you add another planet, instead of just 2 planets, if you have 3, you can't just use period ratios anymore. You have to use a linear combination that looks like this. You can integrate this relation to give an angle instead of a frequency. This is called the critical resonant angle typically. I'm going to call it phi, and here we're using lambdas, which are the mean longitude, basically. So just kind of the position of the planet. And the fact that this commensurability exists means that this angle is about 180 degrees. If it didn't exist, it would just vary over time very rapidly. So what's going on? Why are these commensurabilities interesting in the first place? Well, they're characteristic of resonant chains. So you see critical angles and commensurabilities like this in the Kepler sample, but they're all only in resonant chains. So these are, on the right, are the top 5 that we see in the Kepler sample of the smallest commensurabilities, the ones that are closest to 0. 4 out of 5 of these are known resonant chain systems that have papers written about them as resonant chains. And then you have Kepler-221 in here, which has no paper and has seemingly no resonances. So we need to figure out what the problem is. Why is there no paper? Why are there no resonances? So one thing we found very quickly is that this sort of commensurability could not have formed by convergent migration through it. So typically in orbital resonances, you can just push planets together, and then once they encounter the resonance, they stay in it. But that doesn't happen for this sort of 3-body resonance. It's not strong enough, it's too narrow. Whatever it is, it's not able to form as is. But what it could have happened is it could have remained after diverging from a different set of resonances that is an exact 1, 2, 6 chain of resonances. So that's where you have the 3 planets, you have one in a 2-to-1 resonance, and then one in a 3-to-1 resonance, the next one. And if you diverge those resonances, which I'll talk about in a second, you could have formed the current system of Kepler-221. So it looks kind of like this, where as you apply eccentricity damping, which is a type of energy dissipation, the orbital period ratios actually increase. So if you started at orbital period ratios of 2 and 3 between planets B and C and planets C and E, then over time, those orbital period ratios increase to their present day values of 2.035 and about 3.25. And so we can think of this system as having started in this exact resonance and then having diverged quite a lot from that. But the 3-body commensurability, which is relevant here, is maintained. So you start with these 2-body angles that represent the 2-to-1 and 3-to-1 resonance between a pair of planets. And when you combine them, you end up with the 3-body commensurability that we actually observe. Or you need to get rid of a lot of energy to do that. So energy dissipation is a major problem in the study of multi-planet systems. So there is an overabundance of planets that are just wide of a resonance. So the way you think of this usually is that you start with planets in a resonance, like a 2-to-1 or 3-to-2. And then as they dissipate energy, they move wide of the resonance. And in Kepler sample, in transiting planet sample, we see a lot of planets that are just wide of the resonance. That's what this peak to the left of 0 in this histogram indicates. So you need some sort of method of energy dissipation Usually it's considered to be a tidal method. But the standard kind of traditional eccentricity tides are not strong enough to do this. So if you just have planets that interact with each other and produce a little eccentricity and then interact with the star in a way, because of their eccentricity in their orbit, that's not enough to produce what we see in real planets. But there's an alternative mechanism called obliquity tides, which requires the planets to be oblique. Basically, their spin axis has to be misaligned with their orbital axis. And that's much stronger. But that requires several planets in the system and a complicated type of spin-orbit resonance, which I don't have time to talk about. But the important part is that this has been much more successful because it's a much stronger method of tidal dissipation. But the important thing for Kepler-221 is obliquity tides are hard to confirm. They seem like they're consistent with the data, but they're hard to really check. But Kepler-221 is special because we know how it started and we know how it ended because we know where it is now. That's unusual for exoplanet systems. So we're able to actually get good constraints on the amount of energy dissipation in the system. So we know we've been able to check that eccentricity tides, which were traditionally have been ruled out for most Kepler systems, also definitely don't work for Kepler-221. That's not a huge shock. For reasonable values of tidal dissipation, they're not strong enough. But obliquity tides seem to work well, which is true for the Kepler sample as a whole, but is especially true for Kepler-221 because there are other various clues. So obliquity tides require that the planets are misaligned with each other in their orbital plane. And in Kepler-221, they absolutely are. There's a minimum mutual inclination of something like 7 degrees. It could easily be much more. And the other thing is that when you dissipate this much energy in just 600 million years, because this is a young system, you pour an enormous amount of energy into the planet. So the innermost planet is it's dissipating about half of Earth's insolation in tides kind of continuously. And that might explain why it lies exactly within the Fulton radius gap. It's a very unusual size for a planet, but it may be experiencing an enormous amount of tidal dissipation that could explain that. We're still working on perfecting those calculations to make sure that that is actually consistent. So to wrap up, Kepler-221 is an unusual system, and it could just be a fluke, and then in that case, it's just interesting to talk about, and we'd like to understand its dynamics a little bit. But more speculatively, we might actually be catching the evolution of a super Earth system, watching it assemble or move between some sort of resonant chain and the non-resonant systems, which are more common. Maybe we're seeing something in the middle. But in any case, we have some useful testbed for tidal mechanisms to check here. So thank you very much, and I'm happy to take questions.
All right, thank you. Thank you, Max. That was a great talk. And I know that I already saw people typing out questions for you. So first one here is from Juliet Becker. You mentioned that the system is young. What do you think the system will look like in a few gigayears?
Yeah, so that's something we're starting to look at now. So typically obliquity tides are able to kind of continuously run. So traditional eccentricity tides they become weak after a while, but obliquity tides in many cases just continuously dissipate energy. And so eventually the orbits could be pushed apart in a way that actually generates an instability in the system. And that's something we want to look at more generally, and what happens if you just continue this mechanism for a very long time, and does that look anything like the super Earth systems we see that don't have an observed commensurability?
Okay, and we have one more question from Caitlin Henderson. Great talk and good luck with quals. This is a basic question related to something you said toward the beginning. Not familiar with this area. Can you talk a bit more about whether we expect that resonant change should be more common than is observed from an analytical numerical framework and perspective? Why or why not? And does this depend on, and what does this depend on, planet-planet or planet-star mass ratios? Thanks.
Yeah, so we don't see a lot of resonant chains, and I think the most naive planet formation models produce them very, very often, and it's taken a lot of work to figure out how to not produce them. And so I don't think we really have a good theoretical guide, and we're just kind of looking empirically now. But I think what's happening right now is you can be successful by saying that you can split them into non-resonant and resonant systems, and just figure out, how do you produce the non-resonant ones. But I think there in general aren't enough systems to say anything about statistics with stars. TRAPPIST-1 is probably the most famous resonant chain. TRAPPIST-1 is barely a star, but there are more sun-like stars that also have resonant chains. So, yeah.
Thank you very much. So we're right on time to move on to the next person. Thank you again.